In this video, we'll be discussing about the processing of metallic materials. First of all, let's see the classification of metal alloys. So, metal alloys are classified into two types. One is the ferrous alloys, and the other is a non-ferrous alloys. Then the ferrous alloys are further classified as steels and cast irons. In steels, you studied the iron carbon diagram, in which from zero point 0.3 or 0.2% carbon up till 1.8 or sometimes 2% of carbon is there, and after the 2% of carbon there is no more steel. There is the carbon, the percentage carbon from 2% to 6% almost is cast iron. So in steels we have low alloy steel and high alloy steel, and in low alloy steel we have low carbon steel, we have medium carbon steel, we have high carbon steel. So the low carbon steel we have a plain carbon steel which does not have much of the alloys, and then we have high strength low alloy steel which we have, in which we have a certain amount of carbon with some alloying elements. Then we have medium carbon steel, in which we have plain carbon steel which has only carbon and a very few alloying elements, and we have heat treatable medium carbon steel, in which we usually have mild steel which has certain alloying elements as well. Then in high carbon steels we have again plain carbon steel which only has a high amount of carbon, and next we have tool steels which have which has high amount of tungsten and vanadium, which provides the strength to the high carbon steel. Then we have in high alloy element, in high alloy steel, sorry, we have tool steels again which are used in certain tools and dies, and then we have stainless steel which has high amount of chromium and nickel in that. So in cast irons we have four types of cast irons. One is a grey cast iron, ductile cast iron, or which is also called nodular cast iron, white cast iron, and malleable cast iron. So uh, these are the types of cast irons. Then in the fabrication of metals, again the metal fabrication techniques are classified into three types. One is the forming operations, the second one is the casting operation, and the third one is special kinds of fabrication techniques which involves powder metallurgy and welding. In forming operations we have forging, rolling, extrusion, drawing. Then casting we have sand casting, die casting, investment casting, and continuous casting. All right. So looking to the forming techniques, I'll be just giving you an overview of all these techniques in this video. So in forging, what is happening is in whatever shape you want your part to be, so you will be inserting a metal blank which would be in the form of a rod into a certain die, and the forces will be applied from the top and the bottom. Usually the forces is applied in only in one direction, and your part is to be forged into a specific shape. So this is a forged part has a very high strength than a casted part. um, so all these forming techniques would have a very high strength. These could be done in hot working conditions, that would be in the austenitic temperature or at a high temperature, and these can also be the cold forming techniques, which uh, uh, in which the forming techniques are used at room temperature. Okay. So in rolling, what is happening is your metal blank or your metal billet or uh, a sheet, whatever you want to roll, the thickness or the diameter of your part is being reduced by these two rollers. These can be a high roll, this can be a three high roll, rolling mill in which there is three rollers. So what is happening is there is a compressive stress being provided compressive load being provided to your part, and the diameter or the thickness of the part is being reduced. Next we have extrusion. So what happens in extrusion is that we have a certain amount of die, okay, and this is the die holder, this is the container which contains all the dies. So what happens is we insert our billet inside the container, which is usually done at high temperatures and there is a force being provided from behind from the ram, and from that die your billet is being produced. So you can produce so you can reduce the diameter, or you can, if you want to make any shape, so you can just insert that shape into the die. You can make your die of that shape, and then you can provide the force from the ramp, and your billet would come out with that shape of the die. Okay, so usually these window channels are being extruded, which you can see that there are 4 channels in which from which your aluminum windows are made. So these are done from extrusion. Then we have drawing. In this you are shown a process of wire drawing. So in extrusion you are providing a compressive load, but in wire drawing you are pulling it out, and a tensile force is being applied. So what is happening is there's a die and you have a metal blank or a metal rod or a metal wire in which you want to reduce the diameter or reduce the thickness in normal drawing. So what you'll do is you'll just pull that wire from these dies rather than pushing it from behind in case of extrusion. Okay, so next we have there's rolling. So there is you can say rolling is done from this slab. This is the uh, conveyor roller belt, and you can see that these are 4 high rolling mill in which they have 4 rollers, and your slab is coming from these 2 rollers. So this is hot rolling, and this is done at a very high temperature, usually at the austenitic temperature. And if you want to do a cold rolling, you will do it at room temperature. So this is hot rolling and cold rolling of plate sheets, and if you want to make bars or wires, you can use a billet. And if you want to construct structural sections for railways, and if you want to construct I beams or H beams, so you'll be using a bloom. So a slab, a billet, or a bloom are all the same but has different dimensions. You can see that the slab has a very high surface area, and the thickness is very low compared to the billet, which is very usually square. And the square this is the square dimension here is a very small, usually 6 by 6 inches or 8 by 8 inches, or usually 10 by 10 inches. And the bloom has a very you can say large uh, volume. Basically the volume is same, but the area of the square is very high, and the length is a bit low, or it can be same as the billet, it depends. So this is all. The difference between slab, billet and bloom is just with their dimensions. So you can see that this is a animation for extrusion. So direct extrusion is you're just providing the force from the ramp, and the product is being obtained through the dies. And the indirect extrusion is in which your product is coming out, uh, and you are providing the force from the ramp in this direction, and your product is coming out from the same opening, okay, from the same side, not from the other side. So that is indirect extrusion, in which your product is coming out from the same side from which you're providing the force, and in the direct extrusion, what is happening is your product is coming out from the other side of the die. Then we have casting of metals. So what is being done in casting is our metal is molded and is poured in a mold or a cavity, and it is allowed to solidify. So there are a lot of types of casting in which we have sand casting, we can have a sand mold, we have die casting or a permanent mold in which the mold is of a metal. Then we have an investment casting or lost wax casting in which the mold cavity is formed by a coating of wax pattern with the ceramic materials. When the liquid is metal, when the liquid metal is poured into that mold, so the wax melts because the wax has a very low melting point compared to the metal, and the wax melts away and the metal fills that cavity. And the other we have continuous casting. So in sand casting we have a mold of sand which can be reused. Here you can see that this is a permanent mold casting, or you can say die casting, in which there is a permanent metallic mold which is also cooled down from these pipes, and the metal is being poured into this permanent mold. You can see over here that there is a die. So we'll be closing that die and we'll be providing the metal from the top, and then we'll be removing or opening the die in order to get our required product. Then we have continuous casting, in which uh, there is tonnage from where the molten metal is being provided, and these dies of the castings are water cooled, so that the metal which is provided from the upper part is being continuously cooled, and there are rollers that support the casted part, because it is still very hot, uh, and these rollers are to support the pin in order so that the casted part does not change its shape, because it is very soft at this time and still at a very high temperature. It is solidified but still at a very high temperature, and you know that metals expand at a very high temperature. So it would not be expanding, but it would be very much soft, and it can easily lose its dimensions. Okay, so for that purpose we provide these pinch supporting rollers, which are not providing any stress but just maintaining the shape of the casting. So this is continuous casting. And there is also ingot casting, in which we can which is uh, the same as continuous casting, but there is one difference, as is that in ingot casting our casted part is being obtained one by one rather than continuously. Then we have welding. As you have also done welding in your other course. So welding is basically a joining process. Okay, in which this is the weld metal which is obtained either from the consumable electrode or from the waste metal. This is the heat affected zone, because the heat of this melted part would be uh, transferred throughout the metal, and this would be the most heat effect. This is the very first part which is in which the heat is transferred. So this is the heat affected zone, and usually you can observe the intergranular corrosion in this part, especially in the case of stainless steels. Then there's a concept of hardness and hardenability. So what is basically the hardness of a material? So it is not a mechanical property, but hardness is just a measure of the resistance of the material to indentation or abrasion. So how much your material resists the indents or cracks or abrasion or wear and tear. So that is basically hardness. And hardenability is a measure of how easily a material can be hardened. So hardenability is the ability of a material to be hardened or how easily it can be hardened. So there is a Jomini end quench test which is used for the hardenability measure. So the end quench test means we are quenching the material from the end. So what happens in that test is a test sample of standard dimension is heated to above the eutectoid temperature, which is about 727 degrees Celsius. So basically our material is heated above the above or to the austenitic region, and then the sample is quickly transferred to the text fixture. So this is the text fixture. We'll be fixing this sample over here. As there is no furnace over here, so we'll be just taking out our sample from the furnace and then we'll be fixing it out, and we'll be continuously spraying the water from the water jet from the other end of that uh, our sample. So after the sample has cooled, the hardness is measured at different distances from the quench end. So from this end, the our part will be quenched, okay, and we'll be measuring the hardness from this part to the other end of the part, and we'll be knowing that how much the hardness has been changed throughout. So that is a Jomini and quench test, okay, which was done by a scientist Jomini, and it is basically an end quench test in which we are quenching our part from one end, and we are checking the dimensions after the part has been completely cooled. So in this test, what we obtain is the cooling rate decreases with increasing distance from the quenching end. Okay, so as we are quenching our part from this end, for example, so the quenching and has a distance of 0 from this part, because we are directly applying our water jet to this end, and since at this part there would be the highest cooling rate, and following to the other end the cooling rate would be decreasing. The resultant microstructure along the length can be vary from all martensite to all perlite depending on the time temperature diagram and the critical cooling rate for the particular steel. Okay, so what you can achieve is you can achieve martensite directly from this part, from here, because the part is directly being quenching as the water is directly being spraying into this end, followed by you will be obtaining different structures throughout. For example, here would be martensite, then you can get a benitic structure somewhere, and then going to the right you can observe a very fine and very coarse perlite structure as well. So you can find a variety of structures into your part, and hardness will therefore be decreased as the distance from the quench end is increased. So when the distance from the end quench from here, if you cannot see, I'll just use the laser pointer. From if your distance from here is increased to this is the other end of the part, and this end is being quenched. So as the distance is increasing, the hardness would be decreasing, because you will be obtaining a very coarse perlite, then a very fine perlite, then benite, and then the martensitic structure. So the hardness would be the highest from where the metal is quenched. Here you can see that the graph, that the distance from the quench end, as the distance from the quench is increasing, the hardness values are decreasing. So you can check the hardness on the Brinell hardness tester, the Rockwool hardness tester, or Wicker or Noof hardness tester, depends. And as the percentage of carbon, there's also one relation with the distance from the quench end and the hardness. So you can see that as the percentage of carbon is decreasing, the hardness is also decreasing. Okay, so you can see that this is 0.2% carbon, and this is 0.3% carbon, this is 0.4% carbon, and this is 0.6% carbon. So at the same distance you can observe different amount of hardness. Okay, so you should also remember that as the percentage of hardness, as the percentage of carbon increases up to a threshold, uh, not increasing all the time but up to a threshold, the the hardness values are also increasing. Okay, so the effect of carbon content on hardenability, hardness and hardenability increase with the carbon content. So next we have powder metallurgy, in which compaction of powdered metals followed by a heat treatment to produce a more dense piece. Here you can see that we have two powders. One is of the metal and the other is of the binder. The binder can be in a powdered form, or it may also be in a liquid form. So powder metallurgy makes it possible to produce a virtually non-porous piece having properties almost equivalent to the fully dense parent material. So diffusional process during the heat treatment are central to the development of these properties. So what is happening in the powder metallurgy is we are achieving a fully dense part, which we sometimes cannot achieve from the normal casting procedures, due to the environmental and due to the challenges achieved from uh, the the part geometry on the or the pipe dimensions or the pipe or the part complexity in terms of its shapes. So we can achieve that from powder metallurgy. So what we do is, first of all, we mix the powder and the binder together. We mix it and then we create some pellets of that powder, or we can just get the mixed powders, and then we mold it, put it into a mold, and form a shape, and then we put it into a furnace. When we debind it, we remove some of the liquid part and the other part which is not required. That is called in the green part. And then we do sintering, in which we are the diffusion of the two metallic powders. If you are using two metals, different metals, and make an alloy, so the two metals are bonded together, are mixed together by diffusion, and the binder joins itself, and the part is finally centered, and you can achieve the a solid part. So you can achieve many shapes or many intricate shapes from this powder metallurgy techniques. And in today's world, uh, people are making nano composites or nano alloys from this powder metallurgy techniques, that has a very high strength and are very dense, and you can make any many intricate shapes through this technique. So this again, you can see that how many these intricate shapes are being made from the powder metallurgy techniques. This method is specially suitable for metals having low ductilities. The metals which have a very low ductility cannot being plastically formed or deformed. So we can use powder metallurgy techniques to create this part. Then metals with very high melting temperatures are difficult to melt and cast, since we don't always have the melting facility or the casting facility relating with high temperature metals. So we can fabricate it from the powder metallurgy technique. Other is the part that requires very close dimensional tolerances, for example bushing and gears. So these may be economically produced from the powder metallurgy technique. If we are using the conventional techniques to produce the high tolerance, high dimensional tolerance uh, uh, parts, so sometimes in casting and in sometime in melting, we don't get that uh, particular dimensional stability because of the thermal expansion and contraction of metals at higher temperatures. So this was all about in this lecture. Thank you.